Hello friends, let's continue our lecture on entropy and temperature. So in the previous lecture, or part 1 of this lecture, we defined what an entropy is, or what a change in the entropy is. We defined it as this, wherein we include the external agency, that is heat, and the reference point temperature. So whatever change, that is irreversibility, that is introduced by the heat for a system or to a system that has the temperature T, or that is characterized by the temperature of T. Whatever changes that is introduced to the system by the heat input of delta Q, this change or this degree of change or degree of irreversibility is quantified by the change of entropy, that is ds here. And now, since we related this to the first law of thermodynamics, or the description of the internal energy, which is the change or heat that is fed into the system and work done by the system, and this expression based on entropy can then be written as ds minus p dv. So this is a new expression for the internal energy. One key point of the previous lecture was for a given heat input, the change in the entropy was dependent on the temperature of the system. For a given heat input, if a temperature has a particular or if a system has a particular temperature, the change in the entropy is dependent on that temperature. But that is not the case for internal energy, because we have this T here. So this T compromises or counteracts any effect of the temperature of a system on the change in the entropy. The T here counteracts any effect of temperature on the change in the entropy. Therefore, irrespective of the temperature of the system, when you feed in a particular heat input, the change in the internal energy will remain the same. So the change in the internal energy for a given heat input is irrespective of the temperature of the system. So now let's build on that understanding. So this is our new expression for the internal energy, and this expression, or based on this expression, we can then express the function of the internal energy, a function that is dependent on volume, that is change in the volume, and the change in the entropy. So based on the entropy and the volume, we can rewrite the function of the function for the internal energy. Now, the change in the internal energy, when there is a change in volume and entropy, using of our basic understanding of calculus, can be expressed in this way: change in the internal energy because of the change in the entropy when the volume is constant, plus change in the internal energy when there is a change in the volume when the entropy is constant. So we have an expression for change in the internal energy when we have a change in entropy and change in volume. Now we can relate these two. So this expression is also meant for change in the internal energy when entropy and volume changes. This expression, which we got from the first law of thermodynamics and the description of heat input based on entropy, this also describes the change in the internal energy. So we can relate these two expressions, and it can be seen that based on relating these two expressions, or particularly based on equating the coefficients of ds here, that would mean we have a new description for temperature, which is something like this, or rather so this term here is nothing but the description for temperature. So now, based on internal energy and entropy, we are able to derive at an expression for temperature, or the temperature change that we see when a system changes in a state is what we see is that, or what the temperature change that a system experiences when it changes its states, the theoretical understanding or the theoretical foundation for such a change in temperature when a system changes its states is expressed by this relation. So what happens is that because of the heat input, there is a change in the entropy, and this entropy in turn changes the internal energy. The combination of this change in the internal energy with respect to the entropy would ultimately give rise to the change in temperature. So in the initial or the first lecture on internal energy and temperature, we introduced temperature as a factor that indicates the change that indicates a change of state exhibited by a system. So that is how, if you remember, if you could recollect, we introduced temperature. In thermodynamics, the temperature is introduced as a factor that would indicate a change in the state of the system. The theoretical understanding of how this change happens comes here because of the change in the entropy and the subsequent change in the internal energy. When we relate these two, this is what gives us the ultimate change in the, or this was what gives us the temperature that is associated with the system. Now, so we have derived an expression for internal energy based on entropy, and we have described the temperature, or we have now arrived at a description for temperature based on the internal energy and entropy. So now, if you could remember, if you could recollect, the reason we were talking about, we brought about entropy into this discussion on high temperature material is because the entropy shows us the degree of change. When you increase the temperature of a material, there is a change in equilibrium points. So it changes from the heat input that you give into the system in order to raise the temperature, at times changes the equilibrium position of the material, and the system reaches a new equilibrium point. And to discuss or to show or to quantify this change in the equilibrium position or this change in the irreversible transformation of the system, we introduced entropy. But when we talk about phase transformation, we very rarely talk about the change in the equilibrium points. This change in the equilibrium points, if you could relate it to the first lecture, we brought that because we were not so much exposed to the free energy concept in this course. We want to have a generalized description for the change in the phase transformation, and that is why we described phase transformation as a change in the equilibrium position or equilibrium points. And this change in the equilibrium points is introduced by an external force, and that is the reason and that is how we introduced entropy in the previous lecture. But now we want to arrive at a definite condition that would enables us to predict if at a given temperature will the state of a system change, or will there be any phase transformation, will there be a new equilibrium point present. So we want to arrive or describe a function that would allow us to tell if given the change in the temperature will there be a new equilibrium point for the system. So let us try to derive at such a function. Now again, as a starting point for deriving at such a function, let us begin by describing the change in the internal energy, which invariably happens if you raise the temperature. Invariably there will be a change in the internal energy, but will there be a new equilibrium position, or can we identify, or which function helps us to identify if there is any equilibrium position, or will a new equilibrium position will develop, or will there be a irreversible change, is what we are trying to study, or is what we are trying to derive at. So to begin with, we will start with the change in the internal energy of the system, which invariably happens, and this expression for this is given by like we have derived it based on entropy as something like this. Now in this expression, it is important to know that there are two constants that is involved in this description of the internal energy, and two variables that are involved. So the two constants that are involved are temperature and pressure. The two variables that are involved are entropy and volume. So in this description of the internal energy, temperature and pressure are constant, whereas entropy and volume, they are variables. Now let us assume a system for our intents and purposes. Let us assume a system wherein the change in the volume is constant. Then that would mean that when the change in the volume is constant, and that would mean that dV will be 0. So the change in the internal energy of the system when you feed some heat into it, the change in this internal energy of the system is solely dependent on the change in its entropy. Now, one property of the entropy is that it, as we have described earlier, it shows us the degree of irreversibility. That is how we introduced entropy. So, this change in the entropy is a degree of irreversibility, and that means when these two are positive, that means it is greater than 0. These two are positive, and that means this is greater than 0, which means that for a transformation to happen, meaning if there is a new equilibrium position and then the system moves from its existing position to this new equilibrium position, that would mean that the change in the entropy, since this based on this expression it is greater than 0, it means that the change in the entropy or the entropy increases. Let me reiterate. The purpose of this lecture, or what we want to do is we want to introduce a function that not only tells us with heat input the internal energy or the state of the system changes. We want a function, a thermodynamic function, that shows us with heat input there is going to be a new equilibrium position and the system is going to change from the existing position to this new equilibrium position. That is the purpose of this lecture. We want to introduce such a function, such a thermodynamic function. Now, to introduce that, we have considered a system that does not change in volume, or that has a constant volume, that has a constant temperature, and that experiences constant pressure. And when we do that, we describe the internal energy as this. Now, when we try to look into the description of the change in entropy, that shows that the change in entropy is positive, or the change in the degree of irreversibility is positive. This degree of irreversibility or irreversible reaction is only possible when you have a new minima, when you have a new equilibrium position. So, the condition that is necessary for the existence of a new minima or the existence of a new equilibrium position is the change in the entropy should be greater than 0, or the entropy should increase. If the entropy stays the same, if the entropy decreases with the heat input, let me reiterate, if there is no change in the entropy with the heat input, if the entropy decreases with the external agency, that would mean that there is no equilibrium point for the system to move to. But if the entropy increases, if it is greater than 0, if this expression leads to a value that is greater than 0, which would mean that the entropy is increasing, that means we have a position to which the system could move to from its current position, and that would be its new equilibrium. Now, we can then express this, we can write this expression as du minus t dt is equal to 0, and the entropy should increase. Only when the entropy increases, that would mean that the system has a new equilibrium position, and since this is a negative term here, that would mean that the du, or this expression, should be less than 0 in order to show that there is so this relation here, we have this relation here based on this description or this expression for the internal energy and this condition. These two conditions gives us this description or this criteria, and this criteria has to be fulfilled, or this criteria shows that when the change in the internal energy minus this term, when the change in the internal energy minus this term, when it decreases, when this cumulatively decreases, that means that there is an equilibrium point to which a system can move to. That means there is a possibility of phase change. That means the system will now not only change its states, but will now move to an equilibrium position, or this is the condition that is required for a phase transformation. So, this term here, that is du minus t dt, is nothing but our Helmholtz free energy. So, when you say the free energy of the system should decrease for it to move from one equilibrium to other equilibrium, for a phase transformation to happen, the free energy should decrease. This is where we get it from, and this free energy should decrease or should be less than 0. This Helmholtz free energy should be less than 0, and only then we can say that the system now has a new equilibrium position, and the system will now tend to move to that equilibrium position, and this is being done by a phase transformation or a similar change in the system. Okay. Now what we want to do is we want to see how the temperature affects this function that tells us if there is any new equilibrium position or if a phase transformation is possible. So the whole purpose of this introducing this function in the framework of high temperature material is that we want to know how temperature affects this criteria for describing the existence of a new equilibrium, how temperature affects this criteria for a phase transformation, how a function that helps us to know if there is if an irreversible reaction is possible or not, how this function is being affected by temperature is what our primary goal is in this lecture, and that is why we have introduced this Helmholtz free energy here. Now to understand that, let us consider a simple system. Let's go back to our basics of our thermodynamics, our fundamentals of thermodynamics, and based on a simple system, let's try to see how the temperature would affect the Helmholtz free energy, or can we even get a vague idea of the influence of temperature on the Helmholtz free energy. That is our primary goal here. So let us now, to understand the effect of temperature on this Helmholtz free energy, let us consider a system that comprises of n components. Again, when I talk about system and components, the components in a system, the components here can be atoms, ions, or molecules as well. Now there are n components in its solid state. Let us assume a system like this. There are totally n components, and all these components are in solid state. So we have a system, and in that we have a solid that comprises of n atoms. Let us assume that. And now we give a heat input of Q, and some of the atoms, they gain some energy and they break bonds with this solid system, and they enter into the vapor phase. Again, let us assume a system that comprises of a solid, and that solid comprises of n components. Now you give some heat, or you provide some external, or allow the system to interact with some external agency, and because of this interaction, some of the components of the solid system break away and form or become vapor, but they are again enclosed in the system. Now, just as instead of quantitatively analyzing how much of a change a temperature would have on the free energy, let us try to graphically understand that. So when you have such a system, now the change in the internal energy of such a system is expressed by, and again assuming that the volume, temperature, and pressures are constant, the change in the internal energy of such system is expressed in this way. And now we have the expression for Helmholtz free energy as du minus T ds. Now we have seen, let us focus now exclusively on the vapor phase, and we have seen that the change in the internal energy, or the internal energy, is nothing but summation of the internal energy of individual components. So this was one of our description for the internal energy. The internal energy of a system is nothing but it includes the internal energy of all its components. Now let us consider just the vapor phase, and when you consider the vapor phase alone, let us try to plot the change in the internal energy when number of components in the vapor phase increases. So NV be the number of components in the vapor phase. Let me reiterate, N is the total number of components in the solid system, and NV is the number of components that are moved away from the solid to the vapor phase. So meaning, if NV increases, that means the N is decreasing, and NV is again a part of N, and it has moved to vapor phase now, and we are concerned about the internal energy of the vapor phase. Now if you are concerned about that, then with increase in the number of components, since the internal energy is nothing but summation of all the components, with increase in the number of components, that means there will be a linear increase in the internal energy. So with increase in the number of components moving into the vapor phase, since the internal energy is nothing but the summation of all the components, there is a linear increase in the internal energy as number of atoms move from the solid phase to the vapor phase. Now let us consider the entropy. Now entropy, one of the description for the entropy is that we have a statistical description for it. It means that if there are numerous ways you could arrange the components of a system, that means the entropy of that system is higher. So this is often referred to as configurational entropy. Maybe I don't have time to give you a mathematical expression for it, but please understand when I say that when you have a component, when a system comprises of several components, and if there are numerous ways for us to arrange these components, that would mean that the entropy of that system is high. But if there are only a small number of ways for us to arrange this component, that would mean that the entropy of the system is low. So this is called as configurational entropy. You can search this term configurational entropy in any of the fundamental books on thermodynamics. They would give you a rough idea of it. So to put it even more simply, if you consider a pure element, every atom is identical. You don't have much room to play around with that. You don't have much way to arrange it. That would mean the entropy of a pure element is low. Supposing you allow that pure element to mix with some other element, say A is interacting with B, and now we have new atoms in that system, new component in that system, we can arrange it in numerous ways. That means the way number of ways, that means that entropy now has increased, and this is what I mean by configurational entropy. So if there are numerous ways you can arrange a system, that would mean that the entropy is higher. So imagine if you in the vapor phase there are only few atoms and there are numerous ways you can arrange this atom because there are a lot of vacancies, then it would mean that entropy when the atoms are few is higher. So when the initial stage, when there is a small increase, and there is a small increase in the number of atoms that are moving to the vapor phase, there will be gradual increase in the entropy as well. But when the number of atoms get saturated at the vapor phase, then you would no longer have much of a room to rearrange them. So it saturates, the entropy also saturates. So this is how a change in the entropy looks like when there is an increase in the number of components at the vapor phase. So these are the two graphical representations for change in the internal energy when the number of atoms increases in the vapor phase, and change in the entropy when the number of atoms increases in the vapor phase of the system that is already being shown here. So now let us go back to our expression for Helmholtz free energy, which is nothing but the change in the internal energy minus, this is our expression for the Helmholtz free energy. So it includes both change in the internal energy, which we have graphically seen, but the negative of the change in the entropy. So that would mean if you plot those in the same graph, with increase in the number of components in the vapor phase, we have this linear increase in the internal energy, or rather Ui alone, and we have negative of the change in the entropy. So we have this negative value, so it saturates like that, and this combination of these two gives us the this combination of these two gives us the Helmholtz free energy. So the plot for the Helmholtz free energy would look something like this. So this is the plot for Helmholtz free energy, and based on this plot we could see that there is a minima here, and this is the equilibrium state for the system, and this is defined by the Helmholtz free energy. So now if you assume this expression for temperature T1, that is H1 is equal to, for a temperature T1 we assume that, then this equilibrium position would be pertaining to T1 and it will be equilibrium. Now when I increase the temperature T, when from T1, when I increase the temperature to T2, this would mean that the change in the entropy becomes dominant. The temperature does not much affect the change in the internal energy directly, but it affects the entropy directly. That would mean that this curve would go even further at temperature T2. The entropy becomes dominant at high temperature when it is concerned with the Helmholtz free energy. So this would mean that this curve becomes even more lower, and the cumulative effect and the change in the internal energy, because it's concerned with again with the because of the number of phases, then number of components in the vapor phase, it would remain same. Now this dominant effect of the entropy, this dotted line would be T2 ds, and the solid line would be T1 ds, and because of this new dotted line T2 ds, there would be a shift in the Helmholtz free energy, and we have a new equilibrium position. So we have a new equilibrium position which is even lower than the one that was formed at T1. So now what we can infer from this depiction of the Helmholtz free energy is that the Helmholtz free energy, which predicts or which allows us to visualize the equilibrium position of a system, wherein the internal energy changes and also the entropy changes, when there is a temperature change as well, because of the increase in temperature or the change in temperature. Here it is increase in temperature. Because of the increase in temperature, the dominance of the entropy increases, and this will ultimately shift your equilibrium position, and that would mean that now we have a new equilibrium position because of the increase in temperature. So what the Helmholtz free energy allows us to do is, it allows us to, at least in this lecture, it allows us to visualize the minimummost point or the equilibrium position of a system, wherein when the system is exhibited to, or when the system is exposed to a change in the internal energy and also to a change in the entropy. Now when the temperature of such a system changes, then the entropy or the dominance of entropy increases, and that would shift this equilibrium position to a new position. So ultimately, again, the bottom line of such an expression, or looking into the expression for free energy, particularly the Helmholtz free energy, is that when every other factor remains constant, when the temperature of the system increases, the entropy will also increase, or the role of the entropy will also increase. That would ultimately mean that there will be shift in the equilibrium position of the system. That would mean that the lowest point in the curve of Helmholtz free energy will also shift, and that would ultimately propel a change in the state, or a irreversible change in the phases, or irreversible change in the state of the system. So what we have ultimately done in this lecture is that we have introduced entropy. We have seen that the degree of change in entropy is dependent on the temperature. At high temperature, the degree of change in the entropy is reduced when you compare it with the ambient temperature. But such effect is not observed in internal energy, irrespective of the temperature, be it high temperature or be it ambient temperature, irrespective of the temperature of the system. The heat input effectively translates into the change in the internal energy. And finally, we have derived at a condition, or we have derived a condition that enables us to know if a change, if an increase in the temperature would actually introduce a new minima, a new equilibrium position. We have arrived at a condition through the description of Helmholtz free energy, and we have seen that with increase in the temperature, the minima of the Helmholtz free energy, it is possible for the minima of the Helmholtz free energy to change. So these are the theoretical underpinnings of a phase change that you see when you rise the temperature, of melting that you see when you rise the temperature. The theoretical aspect of it comes from both thermodynamics and also statistical mechanics. I hope you are clear with this discourse, and I hope I have made things clear to you. One advantage of having a flipped mode of lecture is that you can listen to this any number of times you want. If I have made any mistakes, you can let me know. Maybe I will try to correct it. Please, if it is convenient to you, you can also listen to it in a higher speed. So please let me know if you have any question pertaining to this. I will try to address it before the next lecture, wherein we will look at the effect of temperature in the theoretical factors that govern or that influence the effect of temperature in other behavior or other behavioral changes that is exhibited by the material. So thanks again for your time, and let's see ourselves in the next lecture. Bye.